Okay. Hi guys. Good morning. Hope you're all doing well. Are you? Ah, only three of you are there. Very good. Very good. Very good. Okay. Are you guys ready? People are there. We'll wait for 2 more minutes. Start. Okay, guys, we'll start. So I think last class I just gave you an introduction about colloidal state, isn't it? So we saw what are the different types of matter. Like matter can be broadly classified into pure substances and mixtures. And I told you pure substances are going to be made up of single entities, and those single entities can be either atoms or molecules. And depending on whether it's atoms or molecules, I'll be able to call the pure substances as elements or compounds, right? And then we went on to see what are mixtures. Mixtures are going to be made up of two or more, say adding two or more pure substances, right? So again, mixtures can be of two types: homogeneous, heterogeneous. In homogeneous, I have two solutions. In heterogeneous, I have suspensions and colloids, right? So, and the only way by which we'll be able to differentiate between your true solutions and colloids is that by the help of particle size, right? So I told you, if you can remember, the particle size in case of colloidal solutions will be 1 nanometer to 100 nanometer, right? So if at all you see that the particle range is in this between these two values, I'll be calling them as colloids. And the main difference between true solutions and colloids is that you will not be able to see the particles of true solutions as well as colloid with the naked eyes. But if I use a microscope, right, I will be able to visualize your colloidal particles and not the true solutions. True solutions are still smaller, right? So you will not be able to visualize them in the very powerful microscope also. But in colloids, yes, I will be able to see them under a microscope because they're a little bigger in size. And obviously, suspensions are going to have way more size. I'll be even able to see them with the help of naked eyes. I don't need a microscope also, right? So then we went on to see what are the components of colloid, right? So just like how you have solutions have solute and solvent, okay? Even colloid, I think someone has to. Lakshanya. Lakshanya. Can somebody text her if you have your number? If you have a number, please text her. Ask her to mute herself. Lakshanya.
Yes.
Lakshanya, are you there? Can somebody text her? Does anybody has Lakshanya's number? Should be fine in some time. Cool. So as I told you, right, how solutions have solute and solvent. Just like that, I have two components present in my colloidal solutions also, right? And those were what is called as dispersed phase and dispersed medium. Lakshana, you can just mute yourself. Audio problem, I understand. Just mute yourself, please. Good. Cool. Right. So what I was telling, so dispersed phase and dispersed medium, right? So we saw, right? Dispersed medium is what is considered as my solvent. I say DM corresponds to dispersed medium. So dispersed medium is my corresponding to solvent, and dispersed phase corresponds to your solution. Sorry, solute, right? And both of these together make up your colloids, right? So again, how we have in case of solutions, it is not necessary that I need to have only one solute or one solvent. I can have more than one also. Here also it's the same thing. I can have more than one dispersed phase, more than one dispersed medium. But again, in our syllabus, we have only one dispersed medium and one dispersed phase, right? So things are going to become a little easier since I'm going to consider component of a two component system. There is one dispersed medium and one dispersed phase, right? Okay. So if I go for, so what and all we'll study after this is first we'll start with classification of colloids. What are the different types of colloids I have? That is the first thing. And second thing is we'll be studying about how to prepare the colloids, right? How to prepare them. And obviously if you prepare them, obviously purity will be a concern, like they will not be of much purity. So I have to go for purification of that, right? So we'll see what are the different purification processes available. And then we'll move on to see what to say, the properties of colloids. There are going to be certain special properties only colloids have, and none other, like say true solutions or suspensions will not have, right? And obviously the application part of colloids, right? So all these things will be studying. So we'll quickly move on, right? So there are various ways by which you can go for classification, right? Say the first classification is based on classification based on the phase, or say the phase of dispersed medium and dispersed phase. I'm talking about which phase the dispersed medium and dispersed phase are, like it's in solid state or whether it's in liquid state or gaseous state. I can have so many combinations, isn't it? Right? So depending on these phase, right? For example, if you see that the dispersed medium, right? For example, the solvent, like I should not say solvent, but just for your understanding. But if at all you see that the dispersed medium or solvent is water, right? So that means you are dissolving everything in water. So in that case, it is going to be called as hydrosol. Like, hope you understand, right? Hydro means water. Sol talks about colloids, right? So like that, depending on the phase of your dispersed medium and dispersed phase, you will be able to categorize colloids into so many categories, right? So we'll see what are these, right? Say I'll just make a small table, and it is very important, people. Like sometimes easily you can get 1 mark question from the table which I'm going to give you, and this table is available in your book also, right? If you want, you can take down, or it is better to take down just an idea whatever you want to get, right? Say first dispersed phase, dispersed medium, the name of the colloid, and some examples, right? So these are the columns which I'm going to have. This, right? Say starting with solids, if my dispersed phase is solid, and if dispersed medium is gas, Now look at this. I'm telling that the solvent is a gas, right? In a gas, solid particles are embedded there and there and there. What can you think of? We'll talk about the name later. Can you think of any example for this, guys? Can you think of any examples? Solid particles are there in gases. Any example can you think of? Hello? No examples. What do you see in real life? Can't you like just hover your imaginations? If you don't know, tell me at least you don't know. But at least you can tell me, right? Yes, Lakshanya, very good. Dust is a very good example. Smoke is again a very, very good example. What do you see in dust or smoke or whatever it is? In say, for example, if I say dust, right? So what happens there? The medium in which the particles are there is gases, atmosphere, right? So in atmosphere, I have there and there some dust particles. The solid particles are embedded there and there, right? Same goes with smoke, haze, I would say haze or fog or mist comes under another category, right? So basically, if you see that, if I say for fog or mist or whatever it is going to be this. It is actually going to be liquids dissolved in gases. Or say the dispersed medium are gases. That is understood. But the dispersed phase is liquid. Obviously, it's water droplet, fog or dew or mist or whatever it is. It is basically water droplets there in gaseous phase. I mean, in gaseous phase is the total medium, and that water particles are embedded there and there, isn't it? So, example for the first category, that is solids in gases. Examples are your dust and smoke, right? And obviously, I have to give some name to this. So, these are what are called as aerosols. So, you can see aero means air, gas, right? These are what are called as aerosols, and these are also called aerosols only. There is no distinction between them, right? So, the moment you see dispersed medium as gas, you can definitely name them as aerosols, right? An example for this, just now you told me, it's fog, mist, right? All these are very good examples. Cloud, I mean, cloud is a very good example. Clouds are basically gases, and that water droplets are embedded there and there, right? Okay, so that's the second category, right? Now, third category, say I go for solids in liquids. So here I told you here what to say. Right? So here I have the dispersed medium to be liquid, the dispersed phase to be solids. Now these are the most common type of colloids, right? These are like say solid dissolved in liquid. That's the most common type of solution also you have, isn't it? So here also it's the most common one. So they are generally called as sols, SOLS. That's the name of the colloid, right? And obviously, if you look at the examples, there are so many, right? Say gold sol, right? I have astatine, sulfide, right? Even starch, gum, I would say gum. All these are examples for your sols. Okay, moving on. So next, when I have liquid in liquid, that is both the dispersed phase and the dispersed mediums are liquids, right? Can you come up with examples for this, people? Any examples you can think of, liquid in liquid?
I think it's called an emulsion. Is that it's
Yeah, it is called an emulsion. Very good. The name of the colloid is what is my emulsion? True. Examples?
milk and oil, or I remember.
Exactly. Yeah, exactly. So milk is a very good example for this. Milk. There are something called as hair creams. Like generally, all creams. All these are the examples. Okay, fine. Next, when I have gas in liquid, right? That means the dispersed medium is liquid. Okay. Yes. Can you think of any examples? I have gaseous particles in liquids. So the best example I can give you is any kind of foam wherever you see in Tamil, we say norai, right? Say, obviously, we know, like if you would have washed clothes ever in your life, right? Or at least you would have seen your mom washing or your servant washing, you would have seen a lot of this froth coming, right? So froth in the sense, they norai, the Tamil, they say in Tamil, right? So that is what is here, right? So obviously, the moment you touched it, it is going to go, right? So it's basically because the dispersed phase are gases. That's why it just escapes, right? So anyways, so whatever kind of foam you have, so generally these are what are called as foams. The name of the colloid itself is a foam, right? Say any kind of froth, you'll be able to get. I mean, the example would be that, right? Okay, fine. Next, when I have solids in solids, right? I have solids in solids, right? So it's very simple. It's going to be called as solid sols, right? And the examples would be gemstones, some alloys also to some extent, right? Gemstones, alloys, all these can be examples, right? And then I have yeah, liquid. Oh, the moment you see solid, or whether you see gas in solid, this is also called as solid sol, but the example would be different. Here you have foam, rubber, and you have something called as pumice stones. Right. So all these are the examples. Did I miss anything? Yeah. So these are all the examples. These are all the names of the colloid along with the dispersed phase and dispersed medium along with the examples. Everything you must know, people. Right. So sometimes easily you'll be getting 1 mark from this if you just remember all these things. And obviously they'll ask you with examples if they ask you. Right. Cool. So this is the first way by which I'll be able to classify, simple classification, right? Based on the phase in which the dispersed medium and dispersed phase exist. Right? Depending on that, so much classification along with their examples are there. Cool. So we'll move on to the second classification, second type of classification. On what basis we'll do the classification, we'll see that. Okay. Right. Okay. Next is classification based on how do I put it? Based on how they are formed. So it's a very general statement, right? How, based on how these molecules, how these colloids are formed, or I would say, in other words, what is the size of the colloids? Depending on that, also I would say this is the classification. So under this, I have 3 things, right? So I have first one is what is called as multi-molecular colloids, and I have something called as macromolecular colloids, and the last one is what is called as associated colloids. Okay, right? So what is the difference between these two, if you ask me, right? So obviously, for to make up the colloidal size range, right? Obviously, there should be some aggregate of small particles, right? So that is what is told here, multi-molecular. So that means so many molecules will come together, right, to form the size in the colloidal range, right? To form the size in the colloidal range, right? So these are the smallest sizes. So these are among the three, these are the smallest. Okay. Now, when I go to macromolecular, the best way to put it is so many multi-molecular colloids aggregates to form macromolecular colloids, right? So many multi-molecular colloids come together to form macromolecular colloids. Okay, and lastly, when I go to associated is the biggest of them all, right? So again, in simple words, I can say that so many number of macromolecular colloids will come together to form associated colloids. But guys, right? There is no proper distinction between multimolecular, macromolecular, and associated colloids, right? And the questions based off them are also very rare, right? Just because I don't have the proper segregation between these two. The definitions are not proper enough, right? The questions coming from this is also very rare, right? So they can just know the name, right? Based on how they are formed, multimolecular, macromolecular, and associated colloids. If you're really interested in how to know this, you can very well know it. You have the internet with you, and you can always ask me whatever the doubts you have, right? So for now, you can just know what are the names associated. That is 3 types based on that: multi, macro, and associated colloids, right? Cool. So that is the second classification. We'll move on. So next classification is based on whether how to put it. Okay, based on the interaction, the strength of interaction between dispersed phase and dispersed medium. Okay, so this is again just for you to understand what the classification is based on, right? So if I say that it is about the strength of interaction, there are 2 ways of looking at it, right? So we have 2 components here: dispersed phase and dispersed medium. So there can be 2 possibilities, right? Say one, it's like love marriage, right? So you want to be with someone, you really love them, and then you be with them. And then second case is where I have arranged marriage. You don't even know, you may hate, right? But still you be with them just because you got married, right? That's the best example I can come up with. So the thing is, it's all about whether the dispersed phase and dispersed medium are in love, right? Or they hate each other, right? So that's what is here, right? So the category, there are only 2 categories under this. So first one is based on whether the dispersed phase and dispersed medium are in love, or they're going to hate each other, but still they stay together somehow, right? So that's the whole point. So based on that, again, I have 2 types. So first one is what is called as lyophobic colloids. The second category is lyophilic colloids, right? So lyophilic, I think from the name you can understand phobia, right? Girls phobia or boys phobia. So lyophobic means the dispersed medium and dispersed phase hate each other, right? I put a cross mark indicating that they hate each other, but they still stay together, right? And lyophilic obviously is easy, like it's happily ever after. So it is dispersed medium and dispersed phase. Okay, please bear with my symbol. I'm not good at it, right? So dispersed medium and dispersed phase love each other, right? Okay, so this is a very say in a nutshell, this is how I have to put it. Right, dispersed medium and dispersed phase, whether they love each other or whether they hate each other. Based on that, I have lyophobic and lyophilic colloids, right? Okay, so obviously, if I speak in terms of stability, right? If I speak in terms of stability, obviously, who's more stable? Obviously, the people who are strong together are more stable, isn't it? So obviously, my lyophilic colloids are always more stable than lyophobic colloids. Okay. Or I would say, let me put there can be a lot of times where you will be asked differences between lyophilic and lyophobic. So we'll just do it. So lyophobic and lyophilic. I'll just bring out some examples. So the first, first I'll bring out the differences. The first example, the first point of difference is this. This can be the first point, right? So in lyophobic, what happens? In lyophilic, what happens? That's the first point of difference, right? Now, second thing, right? They are. It is very. It is prepared. It is very tough to prepare a lyophobic colloid, right? So I would say they are prepared indirectly, not by direct methods. Like you will see what are all the methods available. And don't worry, you will see what are all the methods available for me to produce the colloid or prepare the colloid. None of these methods can actually be used to produce lyophobic colloids. You can use them to produce lyophilic, right? But lyophobic, it is pretty difficult to prepare them. So we prepare them indirectly. And here it is easy to prepare. Okay, here it is easy to prepare, right? So next thing, when you prepare them, right? Actually, when you prepare them also, like it is not only in the case of basically what you do is when you prepare, you will be adding something called as stabilizing agents, right? And especially you will do this with your lyophobic colloids because lyophobic colloids are going to be really unstable, right? So whenever you produce them, in order to keep them stable, you will be adding some stabilizing agents also, right? So I hear stabilizing agents are needed. Here it's not required because they're already stable enough, right? That's the second point of difference. Third point. Right, so third point would be in case of stability, obviously. So here it is very less stable, and here it is highly stable. Right, and then I would say, what are the differences I can have? Yeah, and yeah, here it is. Lyophobic is irreversible, and lyophilic is reversible. What do you mean by reversible and irreversible? It's like you will study when I go through this chapter, you will study that I will be able to convert your colloids into precipitates, right? Like because again, precipitates are almost suspensions, isn't it? So precipitate, you will be able to convert colloids into precipitates. Okay. So the thing is, I'm telling that lyophilic is reversible. That means what? If once I convert my colloids into precipitate, again that precipitate can be converted back to your colloids. Are you able to understand? So basically, this colloidal state can be reversible with your precipitates. That is when first you convert colloids into precipitate, right? It is easy for us to again convert this precipitate back to colloids. That happens in your lyophilic type, right? But lyophobic type, once you convert, that is, say you do something and then you convert the colloid into precipitate, again going back is not possible, right? So that's why I told it as irreversible. But here colloidal state and precipitates can be interchanged. It can be easily changed with each other. But here you will not be able to do them. Once you convert into colloid into precipitate, you're done. You'll not. There is no going back, right? So that's why I say it is irreversible and reversible. And obviously, you need to know some examples for both of them. So for lyophilic examples would be gums. I would say all your proteins to some extent. I would say proteins and even your starch. All these are very good examples for your lyophilic, right? And lyophobic, you would have seen some examples here itself, say AS2S3, gold sol, FeOH thrice, sol, right? So all these are good examples for lyophobic, right? So 1, 2, 3, 4, 5, and all of the examples, you have 6 points. So this 6 points has to be there in your fingertips. You usually get marks, 2, 3 marks. Easily you'll be able to get if this question comes. Okay, right? Fine. So that's about lyophilic and lyophobic colloids, and that is about the what is that? That is about your classification also. So you saw three different ways by which I'll be able to classify colloids. First was based on your phase of dispersed medium and dispersed phase, and second thing was based on how these are formed, and third thing is this, whether they love each other or whether they hate each other. Based on that, I have lyophobic and lyophilic. Okay, cool. So moving on, right? So we are going to see what are all the methods by which I'll be able to prepare your colloids, right? What is the time? Right. So we are going to see methods of preparation. Right. Okay. So there are broadly, I'll be able to classify the methods as say dispersion methods. But again, it's not a good way of saying it. No, we'll not see it like this. Okay. Fine. So first, under it is what is called as mechanical dispersion. Right. So this is very easy. Okay. So this is your what is that? What chapter is this? Your metallurgy chapter is over. General methods of principles of metallurgy, whatever the name of the chapter is. Is that over for you, guys?
Yes, sir.
So you would have studied froth flotation there. Did you study?
Yes, sir.
Right. So in froth flotation, you would exactly know what, like, that is exactly what you're doing here. Okay, that is exactly what we are doing here. So what I'm going to do is, so I'm going to have the dispersed phase and dispersed medium given into some vessel, right? And I'm going to have constant stirring happening, right? How you like, I don't know, have you ever seen preparation of butter from curd? Churning, they call it, right? So that's exactly what we're trying to do here. I know butter is also a colloid, right? Butter is a very good example for colloid. So this churning, or say this rotating paddles and all these, this is a very good, like very simple method. The dispersed medium and dispersed phase are added to this, and obviously, like for depending on the colloid, so many other different substances can also be added. For example, say in your froth flotation, you will be adding what is it? Depressants, froth stabilizers, and all that. So here also I can have so many things happening like that. But again, and generally speaking, only these two are added, and I have a stirrer or rotator, whatever it is. This will convert the dispersed medium and dispersed phase separate. They were individual entities before. Now they will become together to form a colloid. It's very simple. The best example I can take is churning or your froth flotation. Froth flotation as an example, right? So that's your mechanical dispersion, right? Next is what is called as peptization, right? So peptization is a very simple thing. It is a process of converting precipitates into colloids. Very simple. I told you, right, in case of lyophilic, like lyophilic and lyophobic, I told you that you will be able to convert colloids to precipitate, and especially in case of lyophilic, you will be able to convert even precipitate into colloids, right? So definitely that's the process here, right? And there'll be something called as peptizing agents, peptizing or peptization agents, peptizing only. Okay. So there's something called as peptizing agents, right? So these peptizing agents are nothing but they'll be electrolytes, right? So they'll generally be electrolytes, and they will be added in required amounts to the precipitate, and they can convert precipitate into colloids. Okay. See, it is all about reducing the size of the particles, isn't it? Precipitates are relatively larger in size, right? And colloids are relatively less, like say, smaller in size. So definitely there's going to be doing something with electrolyte so that the size of the precipitates reduces, so that it is going to go into the colloidal range. That's what is happening. So that's about peptization, right? Peptization is the process of converting precipitates into your colloids, and there will be something called as peptizing agents which will be added, and they will generally be precipitates. They'll generally be electrolytes. Okay, fine. Next type of method of preparation. Right. So third one is the most important one, right? It is what it is called as Bredick's arc method. Okay. Bredick's arc method. Right. So it's like, okay, well, I directly go into the setup how it looks. Okay, so I'm going to have a vessel, say, in which whatever the dispersed medium I want to have, I will have, right? So generally this will be used for producing metal salts, say gold salt, iron salts to some extent. All these, whenever you want to form metal salts, right? Generally this will be used. Okay, so here in the vessel I have my dispersed medium. Okay, so now what is going to happen is I'm going to have say I'm going to have two metal rods. Say for example these are gold rods, right? These are gold rods, and they will be connected to a very high terminal battery, right? They will be connected to a very high terminal, very high voltage battery. Okay, so what is going to happen here is, the moment the electricity is switched on, right? Moment the electricity is switched on, an electric arc strucks, it strucks the metals. Electric arc means a very strong impulse of electric current. You know what is an arc? Like basically, it's like when you've seen samurais and people, they just do like this, you will see a wave, like some kind of, even after they move, like how to put it, if they move, the sound and all will come, right? The arc, right? So that is what is being done here. So an electric arc is created, right? An electric arc is created with the help of a very high potential battery, right? So this arc, what it is going to do is, it is going to get going to be given to the metals, right? And these metals will not be able to take up that much current. So what will happen is, they will start they will start melting, or I would say they might even sublimate, right? So I hope you understand what I'm telling. The electric arc is given to the metals, right? So much heat is produced, heating effect of electric current, right? So much heat is produced. So by that, what is going to happen is, either these metals are going to sublimate or they are going to melt, whatever it is, right? Either they will sublimate or they will melt. And if they undergo sublimation, that is, if they become gases, what I do is, above this I have some kind of setup, right? Above this I have some kind of setup, and these will be condensed, to go into the dispersed medium, right? The gaseous particles there in the metals, right? I mean, metals in gaseous form. Once the arc is struck and they got sublimated, they will be in your gaseous state, and then I'll do something to condense them, right? I'll do something to condense them, so that they will go into the liquid phase, and then they'll go into the dispersed medium, and they will become colloids. If it is going to be directly liquid phase, if they directly melt, well and good, right? If they directly melt, and where will they go? They will go into the dispersed medium, and then obviously the colloid is formed. Guys, any doubts here? Again, I repeat, electric arc is stuck, a lot of heat is created, and the metal melts or the metal sublimates. If the metal sublimates, I condense it to go into the dispersed medium. If it directly melts, it will directly go into the dispersed medium, and so a colloid is formed. Okay, right? So that is about your Bredick's arc method. So that's the third preparation. The last one, the last method of preparation is what is called as your chemical methods. Obviously, we are studying in chemistry. How come we don't have any chemical reactions, isn't it? So these are chemical methods, right? So again, under this, I have so many categories based on what type of reaction you use, whether you're using an oxidation reaction, or say you're using a combination reaction, decomposition reaction, double decomposition, all these things, double decomposition, yes, I have. So all these things can come under this. So we'll see examples for one by one. So first I take oxidation, right? Say examples can be H2S undergoes oxidation with HNO3. I know HNO3 is a very good oxidizing agent. So you form sulfur. Now this is my salt, that is my colloid. S, which I write, this is my colloid, and obviously H2O will be there, right? So that is a very good example for your oxidation. And moving on, some can be reduction. Okay, I'll write it here only. Reduction example can be, say, AuCl3 plus SnCl4 will give Au. SnCl4, SnCl2, guys, sorry. SnCl2. So now this is my silver sol, and I don't have space, I'll write it here. Plus you will be getting SnCl4 for this. Plus SnCl4. So again, you can see this can be gold or silver. This can be Au or Ag. Both can be used. So now you can see that through the process of reduction. How is it reduction? Simple, right? Here I have +3 oxidation state. Here I have 0 reduction, right? And here, how is it oxidation here? Here it is -2. Here it is 0. Increase in oxidation number, oxidation. Decrease in oxidation number, reduction. You already studied in your 11th redox reaction chapter, right? So yeah, that's about reduction, right? Next. Is my hydrolysis. Right, say very good example can be the production of FeOH thrice plus HCl, obviously, and this is my colloid. Right, FeOH is a very famous colloid, right? Okay. Next, last one. Now this is my third. Fourth is double decomposition, or even I would even call it as double displacement to some extent, but still, right? So example can be, say, AS2S3, so AS2O3 plus H2S gives AS2S3 plus H2O. So you can see that it is a double displacement or double decomposition reaction. So again, this is my salt, this is my colloid, right? And we should all, one more also is that AGI is also a very good example. Say now I can write that also. I have AgNO3 reacting with, say, Ki will form AGI plus KNO3. So AGI is again a colloid. Right? So yeah, these are all the different methods of preparation. Right? These are the different methods of preparation by which you will be, by which you'll be able to prepare the colloids. Right? So starting with your mechanical dispersion, and then we went on to see a Bredig-Stark method, and before that we saw peptization. And among chemical methods, you have 4 types. That is your oxidation, reduction, hydrolysis, and the double decomposition, or even double displacement, however you want to call it. Right. So these are all the different methods of preparation. So after you prepare, obviously I told you the purity obtained here would be little less. Right. So we have to purify all these colloids. Right. So again, there is going to be some methods of purification. Right. So we'll see what is that. I know this is not one of the most interesting chapters. Even I don't like this chapter much. Right? This is full theory. There is little logic which you can use here. But other things are okay. In this chapter itself, your adsorption and catalysis are little okay. But this part is like this full theory. Okay, so we are going for, we have prepared, we have studied the classification. Now we are going to see the purification part, right? After the purification part, the last part would be the properties, and that's it. We are done, right? So we have the purification techniques, or purification methods, right, of colloids, right? So we have three things under this. So first one is what is called as ultra filtration, right? Okay, so I don't know whether you have seen it. If I'm going to have any colloidal solution, say for example, blood is a very good example of a colloid, right? Say now what you do is you take a normal filter paper, right? So you take normal filter paper and you try to filter the blood. What will happen? Have you? I think you've never done it, but even I have not done it, but still, right? Who will play with blood? So what I'm asking is, what do you expect at least to happen if I pour blood through the filter paper? Will it pass through or not?
It will pass through.
Will pass through, sir.
It will pass through, right? So the thing is, if at all you want to go for say like this purification of colloids, generally if it is going to be a suspension or something else like that, some higher particle size, then I can go for normal filtration itself, right? But if it is going to be true solutions, right, just like how you like sodium chloride solution, all these, or when I have colloids also, right, both of them will actually go through the filter paper. I'm sorry, right? They will actually go through the filter paper. So we cannot use normal filtration, and that's why we have ultra filtration, right? So here the filter paper used will be little different. That's the only thing. The same method, everything is exactly same, but except that the filter paper used is going to be called as an ultra filter paper. It's very simple, right? Ultra filter paper, sorry. Right. So this ultra filter paper is actually, say it is produced from the normal filter paper, and we will only prepare in the lab. Like if at all maybe you do MSc chemistry after this, maybe you will be doing all this. Right. So this filter paper is produced by us in the lab basically. Right. So there is something called as a collodion solution. Okay, there is something called as a collodion solution. Okay. So this collodion solution is nothing but it is 4% nitrocellulose solution. That is what is called as a collodion solution, right? So what you do is you take the normal filter paper and you dip this in the collodion solution, right? You take the normal filter paper and you dip this filter paper into the solution. That is 4% nitrocellulose, or say it is called collodion solution. So you dip it into that and then you dry it for a while, and you are going to get the ultra filter paper, and the filtration part you do with it is what is called as your ultra filtration. Understood? Very simple. I repeat, you have normal filter paper, you dip it in the collodion solution, you dry it for a while, you'll be getting your ultra filter paper, and with the ultra filter paper you go for filtration, and that's it. That is how you purify your colloidal solutions, right? So that is the first method. Second method is this. I think you have heard this. You would have heard this term so many times, dialysis, right? So people who have kidney problems, they say, I'm going to do the dialysis today, right? So what exactly, whatever they do there, the exact same thing only we'll be doing here. So we'll see what is this, right? Okay, so guys, please understand that we are talking about impurities, right? We are talking about impurities present in the colloidal solutions. So generally, these impurities will be metal ions, okay? Generally, the impurities present will be metal ions, which I don't want, obviously. Say, if I have gold salt, right, why should I have Na plus there? It's like that, right? Na plus and Cl minus, why should I even there? So I would say the impurities present are basically going to be not, I would say metal ions, I would say ions, because it can be anions also, right? So the impurities present are going to be basically ions. Okay. So how am I going to on other impurities also? So can we obtain ultrafiltration by stacking up many filter papers over on another? I don't know. You can try and please tell me. That's actually a good question. Right? Please try it. right? If at all you have filter paper, I don't know who was that. 1 second. Oh, who was that? Sachin. Sachin, please try it. Okay, you just stack so many filter papers on one over other and try the filtration. See what happens and tell me. Okay, right? That's nice. That's nice imagination. Cool. So what I was telling, yeah. So the impurities present are going to be ions, right? So we'll see what we are going to do. We'll see this. We'll see the setup. Okay. Cool. So I'm going to have a big vessel, right? So into this big vessel, I am going to have, okay, this is inside this only, I'm going to have the impure colloid. Okay, I'm going to have the impure colloid, and the surface of this, whatever, the bulge, like basically there are two vessels. Okay, this is one vessel, and there is going to be some kind of vessel into which, what is that? The impure colloid is there, right? And the surface of this vessel, that is the surface, the vessel which has the impure colloid, the surface is made up of an SPM. What is SPM?
Selectively permeable membrane.
Exactly. Say selectively permeable membrane or semi-permeable membrane, right? So the surface is made up of a semi-permeable membrane or a selectively permeable membrane. Okay, that means what? Certain particles can go inside, certain particles can come out. That is what is going to happen, and you are going to fill this entirely in water. Generally, whatever the solvent you want to use, you will be able to use. Okay, I'll use water because that is a very good purifying agent, isn't it? Okay, so that's it. That's the setup. Very, very simple setup, right? So now what is going to happen is, right? So I told you it's a selectively permeable membrane, right? So what is going to happen is you will see that the impurities which are present inside, right? The impurities which are present inside, they are going to go from lower concentration. Sorry, this is my higher concentration. The impurities are of higher concentration inside this vessel, and outside this semi-permeable membrane, I have water which has less impurities. Okay, so I am going to have osmosis of impurities happening. So how is it going to happen? From the inside vessel, it is going to go to the water side through the process of osmosis, right? So I would say from this to this, I would have impurities going from inside to outside, right? And obviously, from outside to inside, water particles can go. Say in this direction, water particles can go, and the impurities can come inside. Both side movement are possible. From outside to inside, water. From inside to outside, impurities will come out. And that's it. So the thing is, it is not going to be a fast process. It is going to take so much time, right? So if at all you want a highly pure thing, right, you need to wait for at least 3-4 days. You need to wait at least for 3-4 days if in order. So like at the end of the day, at the end of all this is what you're going to get. So if I bring it out, if I bring the inner vessel out, right, so in that you're going to have the pure colloid, right? Because all the impurities would have gone out, all the water particles would have gone inside. So now if you remove the inside vessel, you are going to see only pure colloid present there. Okay, but the only problem is there are two problems actually. The first problem is that obviously it's going to take so much time, and second thing is you have to keep on changing the water like every 3-4 hours, right? The water which you have inside here, right? So this water has to be changed every 3-4 hours, because at a point of time saturation might happen. What kind of saturation? The impurities will not be able to come out that easily, because I told you it is going to be osmosis, right? Osmosis of impurities through the semi-permeable membrane from inside to outside. So if the outside concentration, that is the outside impurity concentration, if it is going to become higher and higher and higher, the process will become still slower and slower and slower and slower. I know it's already slow. And if you're not going to change the water 3-4 hours every day, every 3-4 hours, the process is going to be very, 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 very slow, right? So two problems here. The first problem is time, and the second problem is changing water. Right? These two are the main problems I have with dialysis, right? But you can ask me, sir, I don't know whether you have any friends or any people you know had undergone dialysis, but I have seen people who have undergone dialysis. It is not like they will go stay in the hospital for like 3 days or not, right? So they will just go 1 or 2 hours, they'll finish it and come back. The same process, dialysis only, the same exact thing. Like what will happen in their, I think, kidneys. So there'll be so many impurities inside their kidneys. So they will try to do dialysis and get the impurities out. That's what they exactly try to do, right? So, but you can, the same thing happens in less than an hour or 2 hours, right? How that happens is because we have a better version of dialysis, right? So we have a better version of dialysis. We are going to make the process somehow faster. That is the third and final way of purification, and that is what is called as electrodialysis, right? We are going to have electrodialysis. So I'm going to use electricity, as the name tells you, right? I'm going to use electricity to make this process faster. Okay. So how am I going to do? We'll see that, right? So please remember, people, this will help, right? I mean, this electrodialysis will help if the impurities, most of them are in the form of ions, right? Because we are doing electricity, we have to do something with charges, right? So definitely, please understand that if the impurities are of the form of ions, yes, this is a very good process. If not, no, right? We'll not be able to use this like as efficiently as we want us to, like. But still, this is a very good method. So move on. We'll see what are the tiny changes. Okay. So guys, this is how it is going to be. So again, it's almost the same setup. This is where I have the impure colloid. Okay. Now it is filled with your water, same thing only, but except that I am going to have 2 electrodes connected. That's it. That is the only difference I have, right? So now, for example, assuming that assuming that the impurity is NaCl, right? Impurity is salt, and generally that's what happens with your kidney people, the dialysis people. They will have so much amount of salt inside their kidneys. I mean, not only that salt, so many different other types of salts. Okay, so that is what they will have. So what is going to happen is the moment, again, obviously, even if you don't have these electrodes, you are going to have normal dialysis happening, isn't it? Obviously, I know this is a semi-permeable membrane. All this, whatever happened, will happen. That is sure. But by the passage of this electricity, by the moment you switch on this electricity, right, what is going to happen? Obviously, say you can see that this is my positive terminal of the battery and is connected here, and the negative terminal of the battery is going to be connected here. So what is going to happen? Just like how you saw in your electrolysis process, the positive charge will move towards the negative electrode, and the negative charge will move towards the positive electrode. And here it is going to become really, really fast because I actually have some attraction. I mean, land-like charges attract, right? So towards this, I would have had, say, this is my positive, so negative charges will move towards this, and towards this, the positive charges will move. And obviously, I'm going to make this particular dialysis process very, very, very fast by the supply of electricity, right? But still, there is one more problem. The problem is still you have to change the water every 3-4 hours, right? The water which you use here, right? That has to be changed no matter what, because again, after a point of time, it will become stagnant. The process will become very, very slow because there is high concentration of water. Sorry, there's high concentration of impurities in the water. Understood, right? So electrolysis is very slow. Just by giving little more electricity with the help of electrolytes, I'll be able to make this faster, 10 times, 20 times faster. That's the truth, right? So that is about electrodialysis, and this is what I would say. Little like this is only will they be doing in your medical practices also, the dialysis process for your kidney patients. Okay, so yeah, that is about your what is that? Filtration. Sorry, your purification methods. So I just require 15 more minutes, people, for us to see about the properties. So that we'll do next class, and I think we'll be starting with solid states also, right? So is there any doubt you want to ask me? Is everything clear?
Sir, will you be uploading the video for catalysis that last class? I missed
Yeah,
it.
they will be uploading. I see. I will not upload. It's the excellent people like Akhila ma'am and Raghav sir will upload, I guess. So you can just ask in the group. Like you have a group, no?
Yes, sir. Yes, sir.
You ask in the group, and they will upload. All the other videos were getting uploaded, right?
Yes, sir.
Then this will also be uploaded. Don't worry.
Okay.
Okay, fine. Thank you, guys. We'll meet again. Bye bye.
Thank you,
Thank you,
sir.
sir.
Thanks.
Thank you, sir.